All right, Math 8. We are starting Chapter 9. Chapter 9 begins several weeks on geometry topics. Probably carry us all the way through spring break or beyond. Chapter 9 is all about transformations, which maybe you've seen in the past, maybe you have not. This first day today, I'm afraid that the notes might be a little bit lengthy. But I think the homework will not be very lengthy. In fact, I think the notes will probably take longer than the homework if you understand the notes well. So try to take good notes. It's a lot of vocabulary, maybe new vocabulary for you, and how to use it. And I don't think the homework will be very hard if you understand the notes. So here we go. We are doing transformations. We have a general definition here for transformations. It is a function or mapping. Mapping's a word we'll talk about that results in a change of position or size or shape of a figure. Transformation is a very general word that basically just means we're transforming a figure into something new, right? And there are many different kinds of transformations. We do 4 of them. A transformation is a rule or function that maps each point of a figure onto its image. It may be described with arrow notation. In just a minute, I will talk about arrow notation. We have another kind called prime notation that is sometimes used to identify image points. And this little mark right here, that is what is known as prime notation. And that little mark is red, prime. In the diagram below, K with this little mark, this would be red, K prime. That is how you read that little mark. K prime is the image of K. So you can see in this diagram that we have taken a triangle and we have moved it over to the right. And in fact, what's happened here is we have flipped it or reflected it over a line in the middle. None of that is too important at this point. What is important is the vocabulary right now that goes with it. So in this transformation, the original figure is called the pre-image. When we want to refer to the original figure, we call it the pre-image. And the changed or new figure is called the image. And a few things to notice here. First up, this is how you write arrow notation. All right? And something I'd like you to know is how to read that. You read that arrow there as maps onto. Maps onto. So this sentence right here reads, as it says below it, I should have just done that. It says, this triangle, JKQ, maps onto, right? That's what the arrow means, maps onto, triangle J prime, K prime, Q prime. So you read those little apostrophe prime, J prime, K prime, Q prime. Notice one more thing, that this would be the pre-image, and the new shape would be the image. And I think that is good for the moment. one more thing. Notice that the letters come, see how the letters in this name, JKQ, come in the same order as the letters in this name, J prime, K prime, Q prime. Corresponding letters need to come in the same order. I'll talk more about that in a second. All right, so the next vocabulary word is this thing known as a rigid motion. A rigid motion is a special type of transformation. It's a transformation that changes the position of a figure without changing its size or shape. All right? That is the key thing about a rigid motion is it does not change the size or shape. Examples of a rigid motion are a translation, which we're going to talk about today, a rotation, or a reflection. An example of something that is not a rigid motion is a dilation. We'll talk more about that another day. So which of the following examples are rigid motions? It says circle all that apply. I think I'm just going to write yes or no. Are they a rigid motion? So the answer here would be yes, because the size and shape did not change. But this one would be no. It changed size. I think over here, these two, the size and shape seems the same, so yes. And I'm a little torn on this one, but I measured them and they seem the same, so I'm going to say yes. No, it seems like the one on the left might be a tiny bit bigger. I'm not sure. All right, so that's all there is to that. A rigid motion. When something is transformed, if the size and shape stayed the same, we call that a rigid motion. All right, so the next thing we want to look at is this thing called arrow notation and how you show things with arrow notation. The first thing I'd like to point out is this here. In the diagram, here's our diagram. It says triangle NID maps onto triangle SUP. And I already know things just from this. Just from this right here. I know that N corresponds to S because they are the first letter in each triangle. And I know that I is with U, and I know D is with P. All right? I already know the letters that correspond to each other just based on the names here, right? Corresponding parts have to come in the same order. So, it says to use arrow notation to answer each of the following. What are the images of I and point D? So here's how I would use arrow notation to show that. Angle I maps onto angle U. I can either look at the diagram and see that I maps onto angle U, or I don't even really need the diagram because I can look at the name and say that since I is the second letter and U is the second letter, they must map onto each other. And I also know that point D maps onto point P. And again, I can tell that from the diagram, or from the names up here. D is the third letter, and P is the third letter. They must correspond to each other. And then I have a second question. What are the pairs of corresponding sides? So I could look over here at the diagram and see which sides seem to go with each other. But the thing is, this is a tricky one. because these triangles are isosceles triangles. Maybe this side goes with this side, or maybe the triangle's been flipped over, and it's possible that this side actually goes with this side if you flip the triangle over. Okay, kind of hard to tell from the diagram, but up here in the names, it's not hard to tell. I can tell which sides go with which sides. I know that side NI must map onto, okay, again, since N and I are the first two letters, they must map onto side SU, the first two letters. Or in the picture, that means this side and this, oh man, so the board just went on me, right? So sad. All right, we're going to have to hang on just a sec. Okay, so the sides that map onto each other are NI and SU, right? And then I'm supposed to name all of the sides, so then I might take the first and third letter, ND, and that's going to map onto the first and third letter, SP, or ND, which is that side, maps onto SP, which is that side. And then last up, the second and third letter, ID, looks like a P, doesn't it, must map onto the second and third letter, UP, so ID maps onto UP. And now I have used arrow notation to show which sides map on to which sides. All right, so you'll have questions on your homework where you're asked to use arrow notation to show what sides correspond to what sides. All right, so next up, we learn about our first transformation. It's called a translation. Sometimes a translation is simply called a slide, because a translation is really when you just take a shape and you slide it across the graph. All right, it looks like triangle ABC up here. If I just slide it to the left and down a little bit, it would match up with triangle A prime, B prime, C prime. This is a translation or a slide. And the first thing we want to learn is the notation for how to write a translation. So, a translation is a transformation that maps all points of a figure the same distance and the same direction. And let's look at how to write it. In general, this is what a translation looks like. We use a capital T, which stands for translation. And in parentheses, we put the shape that the figure we are translating. So this would be the translation, and you actually read the parentheses of. This would be the translation of triangle ABC equals triangle A prime, B prime, C prime. That would be the general notation. Let's look at the specific notation, which also gives us the direction and the distance. It would look like this. I'm going to start here with arrow notation. Sometimes arrow notation is called coordinate notation. And it looks like this. XY maps onto X, minus 3, Y minus 1. So this arrow notation or coordinate notation tells us what happens to each coordinate in the triangle. Like if you started with point A, this tells you what happens to the X value. the new x value of point A is the old x value minus 3. And the y value, the new y value is the old y value minus 1. I'll get back to that in a minute. What I like better than arrow notation is this thing that we call vector notation. A vector in a translation gives you direction and distance. And this is how you write it. We start with a T for translation, and then kind of down here as a subscript, we have what's known as a vector. It looks like an ordered pair, but it's inside these little angle symbols instead of parentheses. And in this case, it would be a -3 and a -1. See how it looks like an ordered pair? And it actually kind of acts like an ordered pair. The -3 is telling us how far to go in the x direction, which is, it's telling us how far to move left or right. Whereas the -1 is telling us how far to move in the y direction, or how far to move up or down. And I will show you how that works here in a second. And I would still put of triangle ABC equals triangle A prime, B prime, C prime. But the really important thing to learn here is the vector. The vector gives you the direction to move and the distance to move. So, the -3 is telling you to move 3 in the x direction, and since it's negative, it's going to be left 3. Notice in the diagram that the pre-image A goes left 3 and then down 1. The down 1 is because of the -1, right? The -1 is telling you how far to move in the y direction, and since it's negative, you're going to go down. This vector means left 3, down 1. And you can see that all the points in the triangle, from wherever they started, went left 3 and down 1. Left 3, down 1. All right? That is vector notation. Notice that the arrow or coordinate notation is saying the same thing. Right here it's telling you do x minus 3 and do y minus 1, which means the same thing as, take your x values and go 3 to the left, take your y values and go down 1. Let's look at how to use this. So for each type of transformation, we want to be able to use the rule. If you are given a rule, can you use the rule? And when, let's see, and when you're given a rule, when you're given a transformation, can you write the rule? All right? I'll go over both of these, don't worry. So, here are the two things you want to be able to do. First, we want to be able to use the rule. I show you a translation rule, you can use it. Here in example A, I have given you a translation rule. Do you know what it means? Well, hopefully you know that this vector is telling you, go left 5 and go up 4. So to use the rule, I would take the triangle that's in the diagram and I would move each vertex, right? A vertex is the corner of the triangle. I would move each vertex by the rule or the vector. And then reconnect them. So I'm going to take the letter C here, and I'm going to go left 5, 1, 2, 3, 4, 5, up 4, 1, 2, 3, 4. Here would be my C prime. I'll do the same thing with B. I'll go left 4, 1, 2, 3, 4. I'm sorry, left 5, up 4, 1, 2, 3, 4. That takes me here to, and I would name that B prime. And I take the other corner, or vertex A, and go left 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, up 4. There's A prime. I would reconnect them. And I have taken my triangle, and I have done a translation. I have taken the original triangle and slid it across the graph, up and to the left, right? How about example B? What is the vector telling you here in example B? Do you know? Well, of course, the 3 is the x direction, and that's telling you to go right 3. And the negative 2 is the y direction, and that's telling you to go down 2. So if you see this rule, could you use this rule? Could you take triangle XYZ and use the rule? Pretty easy, right? Right 3, down 2. So I take each corner and go right 3, down 2. And there's y prime. And I go over here to x, and I go right 3, down 2. And there's x prime. And I go to z and go right 3, down 2. And there's z prime. And I reconnect them. Uh-oh. The board has gone again. And there's my new triangle. All right? Again, I slid the triangle to the right and down. All right, so the next thing would be, if I show you an example of a translation, can you write the rule? Most people find this pretty easy. The important thing to be here would be check the direction. So check the direction of one vertex. I mean, that's really going to be the key to writing the rule. See what one vertex does, and then you can write it. I'm going to look at vertex C. Now, you can't see it, but this is C prime. You can see the A prime and the B prime better. So I want to see what happened. Let's see. It looks like it goes 2 to the right, and then 1, 2, 3, 4, 5. 2 right, and then down 5. So how do I write a translation rule? I start with the capital T for translation, and I put a vector on it. And my vector is 2 to the right, so that would be a 2 where the x goes. And down 5 would be a negative 5 where the y goes. And then I would put of the triangle I'm moving, which is ABC. And there's my rule. Translation, vector 2, negative 5 of triangle ABC. How about you try example B? Example B would be, let's see, let's take point A, and it needs to get here, so I need to go this way and this way, all right? My rule is going to be, I didn't leave myself much space there. Let's try that again. Let's put it here, translation. All right, it looks like I went 1, 2, 3, 4, 5, 6 spots to the left. So that'd be negative 6. 1, 2, 3, 4. 4 spots down. That'd be negative 4. And this time I have a 4-sided shape, ABCD. And there we go. That would be the rule. All right, I got one more for you. In this case, we have to write the rule and use the rule. A little bit tricky. It tells me in this problem that triangle XYZ has these coordinates. And here's the important thing. some translation maps x to -1, 3. And they want to know the coordinates of y prime and z prime. All right, so how are we going to do this without a graph? Well, look at x and x prime coordinates. Look at the coordinates for x and x prime. And think about what happened to the x coordinate and what happened to the y coordinate. So let's look. X was at 3, -5. X prime is at -1, 3. What happened to the x coordinate? Well, the x coordinate went down 4, right? So my vector for this translation, my vector is going to have a -4 because the x coordinate went down 4. What happened to the y coordinate? Well, the y coordinate from -5 to 3 went up 8, +8. So the vector is going to have a +8. This is going to be the vector that takes x to x prime. And I can tell that just by looking at the x coordinate and the y coordinates of point x and x prime. So, what happens to y? Y is currently at 1, 7. Where is y prime going to be? So y prime needs to follow the same vector. The x coordinate needs to go down 4. So from 1 down 4 would be -3. And the y coordinate needs to follow the same vector. It needs to go up 8. It would become 15. Can you get the z coordinate on your own? Where would z prime end up? All right, look at z. Where would z prime end up? Did you get 7 and 21? Hopefully. All right, just 1 or 2 more things. I'm not going to spend much time on this. The question here says, use the graph at the right, write 3 different translations. So I'm going to have 3 different translation rules here. And I'm not going to do them all. I think it'll be self-explanatory. I want 3 different translation rules for which the image of RST has a vertex at the origin. Right? This is the pre-image. I want the image to have a vertex at the origin. 3 different rules. Remember, the vertex is the corner of the triangle. So this is really just asking you, how can you slide that triangle so that one of the vertices, A, B, or C, ends up right here at the origin? For example, if I wanted to move point A to the origin, point A would need to go 1 spot to the left and then down 3. -1, -3. There's the translation rule that would move A to the origin. You could probably do B and C on your own if you needed to. I think there's a homework problem like that. All right, last up is this thing that we call a composite of translations. When one translation is followed by another translation, we call this a composition of translations. All right, the composition of translations can always be described using a single translation. Let me give you an example. I'm going to find a single translation that has the same effect as two of them. So, example A here, I'm doing two translations on this, but you know, I'm only going to do point A. I think you'll get the idea if I just do the two translations on point A. So let's look at point A. And I'm supposed to do a translation with a vector 1, 4, followed by a translation with a vector negative 4, 2. Again, we're just going to do point A. All right. So the first one says, move point A 1 to the right and up 4, right? That's what this one says, 1 to the right and up 4. This would be A prime. Now, if I'd written this correctly, the second one would say A prime. We now want to take A prime and move it according to this vector, 4 to the left and up 2. So that'd be 1, 2, 3, 4 to the left and up 2 would take me here. And maybe we would call that A double prime. That's right, the second one would be double prime. All right, what we're looking for is a single translation that would take us from A to A double prime. So look where A is. Look where A double prime is. What single translation would take you there? Well, that would be this way and up, right? It would be 1, 2, 3 spots to the left and 1, 2, 3, 4, 5, 6, 6 spots up. It would be a translation that goes 3 spots to the left and 6 spots up. So our vector would be negative 3, 6, right? The vector gives you direction and distance. All right, so the rule is the single rule. This is the single rule. It's a translation of negative 3, 6. But I want you to see something. Remember the original vectors right here? The original vectors of 1, 4 and negative 4, 2. Look what happens if you add those together. If you add those together, 1 and negative 4 is negative 3. 4 and 2 is 6. When you add the two vectors together, you get the single translation. An easier way to do it than graphing it is just add the vectors together. So what about letter B? What if we had a translation of 12, negative 2, and then did a translation on that of 1, negative 3? What single translation would be the same? Well, hopefully you got... Did you get it? How about 13, negative 5? If we add the 12 and the 1, we get 13, and the negative 2 and the negative 3 gives us the negative 5, and that would be it. All right, good luck on the homework.